Okay, everybody, we are going to look at some things that will affect your file type, including the file efficiency, file size. A couple of the vocab words that we're going to look at, and you're going to do an exercise on understanding a little bit better, is bit depth, which should be a little bit of a review, aspect ratio, codec, what they are, why they're important. And then we'll finally look at interlacing versus progression. So codecs, what are they and why do we need them? Codec, first of all, stands for compression, decompression, and it has to do with how we crunch the numbers down when we create a movie, but also how we open up that file again and can see what we're looking at. So the things that codecs do, they're basically ways of crunching the digital numbers of your file down, and the types of things that they crunch are your image quality and the speed, how well it runs over time, and also some interlacing or some artifacting that you get from it. And so first of all, we'll look at file size, and the most basic way of looking at file size is bit depth. Bit depth is made up of pixels when you enlarge a single image. And each image or each pixel is made up of a byte or a string of 8 bits. So a grayscale image uses a value scale that's from 0 to 255, or 256 levels from black to white. When we talk about a color image, for the most part, we're looking at 3 channels of grayscales with 256 levels from 0 to 255 with a filter of red, or with a filter of green, or with a filter of blue. And each one of those channels is called an 8-bit system. A grayscale is just an 8-bit system, and a color scale is made up of 3 8-bit systems, or therefore a 24-bit system. And those 3 channels get composited on top of each other, and voila, we get full color imagery. Okay. And so we see these in terms of size. For instance, you may have noticed in Photoshop that if you open up a color image, it's pretty much 3 times bigger than a grayscale image, if you compress it to a grayscale image. And so we also see this when we look at file size. When we look at bits, each bit that's on or off, or a string of 8 bits, is 1024 bytes. And 1024 bytes is called 1 kilobyte. And 1024 kilobytes is called 1 megabyte. And approximately 1,000 megabytes is called a gigabyte, and so on, to a terabyte, a petabyte. Another thing that will affect file size is the aspect ratio. And so if you look at an HD image on the left, you see that the aspect ratio is 1280 pixels by 720 pixels. So that's for high definition. It's 16 by 9, and a file size might be 2.64 megabytes. An SD image, a standard definition video image, that's a 4 by 3 aspect ratio, and it looks a little square, is 640 by, or an example might be 640 by 480 pixels, is 1.2 megabytes. So just from going from standard definition to high definition video, we've created a much more pixels and therefore more pixels per frame, and therefore all the little frames in your movie add up to a much, much bigger file. So aspect ratio and pixel dimension will affect the size of your file. So what does a codec do specifically, or what is the goal? It reduces the file size. That's its job. But in doing so, you want to maintain quality. You want to maintain two things for the most part: the image and the image over time, which are two very different compressions. And one of the ways we use this is called lossy versus lossless compression. So if you can imagine a grid of either one of these images, a black cat on a black background, and imagine a grid with all the little value scales enumerated in each pixel. Well, if 0 is black and 255 is white, then you're going to get a lot of really low numbers. You're going to get a lot of zeros and ones, maybe a 10, maybe the green of the eyes is going to be, 50 or 100 or something. But for the most part, you're going to get a lot of very, very similar pixels. Very, very similar, because you're seeing only a few values in that black cat on a black background. So what the compression will do, the lossless compression will do, is it will look at your pixel map, pixel image, and it will make a map of it, and it will find all the pixels that are alike. For instance, everything that is a 10 value on the value scale, and it will take all of those 10 value pixels and all of those 0 value pure black pixels, and it will, if there's 110 pixels, it will throw them all out except for one. If there's 200 pixels at a 0 value, it will throw them all out except for one. So therefore, you'll just have a few pixels describing that cat, that black cat on a black background. Just really a handful of pixels. And what it will do, it will compress it way, 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 way down and make a really small file. But when it decompresses, because it's saved a map, it will replicate those pixels and it will know exactly where to put them. Okay, so the image on the right, using the same compression idea, will obviously make many more pixels. You have a white background, but then you have primary colors, secondary colors, flesh tones, and it will have to save a lot more pixels to get all of those colors and values, and it won't compress it as much. It will decompress it, and it will still put all the pixels back. And the way these lossless compressions work is they will work in chunks. So they'll take they'll start with the upper left of your image, and it will take just say 10 by 10 pixels at a time, and it will just see a bunch of white, and then it will scan over and over your whole image until it makes these little chunks of maps. And so if you've ever watched CNN or seen overly compressed movies, you'll see these sort of chunky squares in them. And those are images that have been over-compressed using this, or at least over-compressed from an image quality point of view if you can see them. Because the idea of lossless is that you can't tell. It's supposed to put it back the way it looks as the original. But that is sort of the test of compression and lossless. Now, lossy compression is when early compression schemes were really about number crunching and weren't about image quality. And so, therefore, it was just about getting that image down so you could do things with it, put it on a CD, send it over the internet, that kind of things. And the pixels are actually gone and they can't bring the pixels back. So there are different ways and different mathematical strategies of crunching those numbers down without changing image quality. And it depends on your image. It depends on the kind of, if you're doing a slow sunset where the colors are changing very slowly, or you're doing fast action, you might want a different compression. Also, different directors, different artists have different aesthetics, and the artifacting from one compression scheme might be perfectly acceptable to one person while it's aesthetically displeasing to another artist. Okay, so just sort of a little bit of where they come from and why there's so many and why they're kind of complicated. It's not just aesthetics, but it's also who developed the different kinds of compression schemes. And we'll have a look at specific compression schemes. You may have heard of some of these. So you've heard of JPEG, obviously. So the Joint Photographic Expert Group was a group of non-affiliated photographers, professional photographers, academics, and corporate people involved in photography in 1986 who weren't happy with the compression schemes that for the first time people actually cared about image quality in compression schemes. And so they came up with a compatible system that all software could potentially use. And that system, while it's been upgraded over the years, has been had the most longevity out of any compression system that we use. Cinepack had a different origin, and that was actually developed for Apple Corporation in 1991. Had the exact same idea. This was for movies and one of the earliest movie compression systems, but it was proprietary. So Apple came up with it, and you had to use Apple products in order to get it. And so it worked best with the software and also had compatibility issues with a PC, for instance, in the early days. Sorensen, that was developed for QuickTime. That was a different kind of compression scheme. Actually, Cinepack was more about number crunching. Sorensen solved the problem of that chunky artifacting, but it took a really, really long time to actually wait for the compression. And artists who care about quality would use a codec like Sorensen. MPEG is the motion picture expert group by another humble group of cinematographers in Canada. DVC Pro is proprietary by the actual AV equipment, by the cameras. And you needed to use a very specific workflow to use it. So, and then finally is the one that we will use, which is a version of MPEG, which is H.264. And that has proven to be pretty stable and is non-proprietary and is compatible across platforms and workflows. Things that come up are the bit rate, which you'll see these things, bits per second or kilobits per second or megabits per second. And that really has to do with how fast it can transmit your imagery over time. And so you want a high enough bit rate so that your movie looks smooth, but you don't want a bit rate that's so high it's going to make a huge file for you and not make any difference in your quality. Bit rate or data rate, and so you'll see these are how they're measured, and you can see what the recommendations are. This is not something you need to memorize, but it's something you should be familiar with when you see it and know what it is. And we can go over, what you will need for certain jobs. Like we're not burning DVDs or making Blu-rays, but that that megabits have to do with how your file will appear over time. So if you don't like the way your file's turning out, then you might want to go back and look at the bit rate and adjust it, because your automatic settings are going to be pretty good. It's when you're unhappy is when you need to understand these things. Baud rate, similar, is the number of changes per second that can transmit across a data stream, such as an Ethernet cable or Wi-Fi. And here, bandwidth is the actual cabling, including, Wi-Fi would be in that also, or yeah, it has wireless in here. So you can see in the early days, a modem would only transmit 56 kilobytes per second, which is like a Word file, versus an Ethernet cable, which you can see the earliest Ethernet cable was 1 gigabyte per second versus Ethernet cables today, which can travel 100 gigabytes per second, which is why we can do streaming movies. But fiber optics is even 1,000 times faster than Ethernet. So the idea is your movie will play as fast as your slowest connection, if that makes sense, because you may be working off of a Wi-Fi that's using Ethernet, like we are in this building or in the Fine Arts building, wherever you are. And finally, interlacing versus progressive. This is something that's already come up. You've seen it on some of your cameras where they ask you for 1080i or 1080p. They're talking about interlacing versus progressive. And just to give you a little background, because we still will see the artifacting from it, to understand why we see it and what it is. So in the early days of television, it was very difficult to show 24 or 30 frames per second that there would be jittering or artifacting. So the TV people came up with this idea about fields. So when you see something that's 30 frames per second, you're actually seeing two fields of images. And that is every other line is in the first field, and then every other line is shown in the second field. But these happen so fast that you don't see them. They just blink in front of you. Kind of described like, and they fall kind of like a Venetian blind, so that these kind of flap down and then these flap down 24 times a second. So you don't perceive it. And this was so that we could, because in early television days, there wasn't the bandwidth to actually see a whole frame at once. It would come down a third of the way, and then it would just stop, or we would actually physically see it come down. So while we no longer have this issue, we can now look at 30 frames per second, and we can look at the whole frame come down. And we can look at 60 frames per second, and we have fast enough displays to see that. We still have cameras that operate on interlacing, and we will still get artifacting from this technology. And this is what it looks like. So you see how it's bandwidth that usually in areas of high contrast. So you don't really see it on dark, and you see it much less on light, or medium value on medium value, or light on light. But where there's dark on light, you really see it strongly, and there's a lot of motion. You'll sometimes see it also there. And there's a filter to get rid of that when you see interlacing versus progressive. Now, interlacing will give you a smaller file size. It will actually be more compatible with certain workflows. And some hardware is not compatible with progressive. So very often in our workflow, we'll see some interlacing, but in the movie, there's a screencast that will show you how to get rid of it. So hope that helps clarify some things about compression. We'll do an exercise so you can see how to read them.